compressibility effects. And within that we had a definition which is bulk modulus, right? And we had already defined it as dP, and we did something like this. It was volume, but we changed it to density part. And we gave certain examples that in case of water it is really tough. You would require a lot of pressure in order to compress it even by 1%. I think 3120 was the kind of factor which we were looking at, right? Gave you examples about the kind of pressures which you feel once you are in water. So it is because of the water column on your cell, that's why you experience that thing. Okay, next thing is, by the way, how many, I think I've asked it, but just for the record purposes, how many of you know there is something known as a book? Whenever there is a class, there is something known as a book. Everybody knows that, right? And how many really go back and open that thing which is known as book? No one? Can I just copy paste questions from there, and that would be a good thing. I don't have to cook up questions. So that is good. So the things which I specify that go back and look at in the book, please do so. Like table 1.1 is an important table, you must know. And if you think there is some confusion about the book, which version are we following, so please consult and make sure that you correspondingly go to the same table or figure or whatever. Okay, so we have expansion of gases. This is the second topic here. I think we covered it. Did we? No? Maybe it's the other section. Anyways, there are some things which are known as isothermal process, and this I am very sure that you guys have already covered it or studied it during you're already done with thermo? Good. Constant. So pressure with ratio of pressure with respect to density is constant for isothermal processes. So in terms of gases, you can compress them if you heat them, or if there is enough volume available, they would expand as well, right? So this is, and the way they behave is different. What kind of processes you are involved in. If you are allowing the temperature to change, it happens differently. If there are friction involved, then they do things differently. So that's why these different terms you see: isothermal, isentropic process. So if I kind of ask you that what kind of thing is this, there is no heat exchange and no friction losses, right? So once it comes to this kind of process, then you have rho over K equals constant, where K is Cp, good, and there is another relation, Cp minus Cv is, R is, right, ideal gas constant, PV, P equals rho RT, so that R is there, right? So things are kind of interrelated, so that's why question. So if you see these things, they are exactly the same as you had studied before in your thermo and fluid mechanics. Whenever there is a heat transfer going on, or we are dealing with the gases which expand or they are getting compressed, so those same kind of variables, you see them over here as well. Okay, so go to the next one. Let's say go to slide number 2, and next thing is the same kind of examples. Now, by the way, if I, since that is constant, there is one relation, let's write it. In one of the examples, it has something like this, where I is initial, and sure, join in. So if you see expressions like these, or if you have to use expressions like these, you shouldn't be kind of you shouldn't be getting confused. If I give you a few things at initial stage, and I want you guys to compute things at final stage, given pressure or the density, you should be able to compute K for that particular gas, given Cp, Cv. Right? So these are the formulas. I won't give you like already made up kind of problems. You practice these. These are nothing but there are 4 variables. I give you 3, you can give me 4. Right? So nothing fancy in it. But if there is anything in terms of multiple choice or any other short question, you shouldn't get surprised at all. Did we really solve any problem in the class? No, I won't. As long as you get the main concept, that concept will be tried during the exam. Right? You should be able to kind of go over it. Okay, next thing is kind of interesting, which is the speed of sound. In most of the books, whatever kind of books you have, generally chapter 1 gives you the intro part. It gives you fundamental concepts which will be used later on in the book, right? Some of them, they are just to give you a brief idea that beyond this book what can happen. For example, this compressibility, we may not go into the detail because at the end of the day, being mechanical engineers, let's say if we are solving flow in a pipe later on, chapter 8, chapter 9 in FM2. So if it is behaving in let's say a turbulence fashion, so some of the rules which are just introduced here, some of the concepts, they will be applied there in detail, right? And in this case, let's say Mach number, I don't think so we will cover anything which has to do like supersonic flows. I doubt. Even in FM2, once we go to chapters which are in detail, you won't really go, because as mechanical engineers, most of the fluid stuff which you are dealing with, subsonic, so he might just throw away certain concepts which you may not use them later. But chapter 1 is, that's why I'm going slow, just to give you an idea that these concepts, they are, familiarize yourself. If you use it later, good. If not, it's also good, just to get an idea here. Okay, speed of sound. There is a concept and this term disturbance. I'm putting it in quotes because of the reasons. So if you happen to stand on a bridge over a river, and if you're not driving, if you're walking, and if you just look down, sometimes there are funnels sort of structures where on which the, let's say, something like this, and on that lays the bridge, and let's say the water is coming this way, right? And what you see here is kind of stuff. I'm just giving you an example. What is a disturbance? So rest, the water is kind of flowing smoothly here, and then here. But this region is kind of, there is a disturbance here. So the water is coming from here, this side, and it already comes to know that there is something coming. So it kind of gets this way. And you see some kind of water, it gives you a certain idea that things are flowing backwards, right? So if you think of this as a view, from a point of view that there is a disturbance which is there, and it is trying to tell the water which is still coming that, hey, there is a disturbance, adjust yourself, right? Now it really matters that what is the speed of that disturbance. What is the speed of that disturbance? And that disturbance travels with the speed of sound. So that is kind of important. That there is a disturbance, the particles which are coming, they would come to know that, hey, there is some obstacle in front. Clear? So that happens when there is you start increasing the velocity of let's say aircraft, because that can reach supersonic. So the moment you get close to the speed of sound, the aerodynamics is very different. And the moment you are at Mach 1, so that before the particle travels back to tell the aircraft that, hey, there is a disturbance or the aircraft is coming, because in this case we gave the example that water is coming, there is still air, now the aircraft is coming. So the particle which is right there, it would come to know that there is something coming because of those pressure waves which are traveling at the speed of sound. So it can tell beforehand that there is something coming. So the disturbances or the pressures in the air, or let's say in any medium, they travel with a specific speed, and that is the speed of sound. And now what if the aircraft is kind of coming with a speed which is beyond the speed of sound, like supersonic? So the particle, the moment it kind of bangs in the particle, then it comes to know what happened here, right? So that's why there is something known as a sonic boom and all the crazy stuff which happens at supersonic aerodynamics, right? So that's why this disturbances, it has many different connotations, but from fluid mechanics point of view, disturbances are the pressure waves which are generated due to the presence of any obstacle. Clear? Okay, so we have the velocity. Let me kind of write it. Okay, it's tough to write here, so where is it? The velocity at which these disturbances propagate is called acoustic velocity. So this is in the book which I have, the kind of version, it is chapter 11. It goes further ahead and discusses these things, right? So next thing which we have is this C, which is speed of sound, is kind of related with dp, this dp d rho, the way it is defined. Change in pressure and density of the fluid medium through which it is being propagated. So this is kind of the governing equation, and then we will see that how that relates. Let's go to the next slide. Go to slide number, let's say 3. And we already said something about dp d rho is defined as, and there's an extra rho as well. So if you do a little bit of mathematics, so in terms of the bulk modulus, we have C equals, it's dV is in fact bulk modulus, right? And there is a rho which comes here. So this is what it is. So if we can say, since since disturbance is small, then heat transfer is also negligible. And we kind of trying to define this process as entropic if this happens. But let's say if there is, how should I make it? This is the aircraft wing, and the air is coming like this. So somewhere here it also develops, which is, let's switch colors here. We call this as, let's say, a shock wave. Here, if it is like a supersonic, it's a shock. Question? Wing. It's kind of at an angle. This is kind of the fuselage. Wing. So this is kind of a shock, and what happens is that across the shock, temperature varies, pressure varies. So there is a sudden change either in temperature, pressure, so all these properties of the fluid, they change drastically. That's why it is known as a shock. Okay. And where am I? Okay. Let's go back to black. Okay, so for gases, isentropic process, we have as Kp. So, and you do this maths. There is kind of putting this equation into that equation, that equation into this equation, you should be able to get this. So if I ask you, show that this is equal to this, you should be able to do it. And once I have this, you should also do this. What is the equation which I have used here in order to get this? Right, P is equals rho RT. Nothing fancy, but those things which are already known to you guys, you can just plug them in and you get the answer. Clear? Okay, just for the sake of doing something, as an example, although I said I'm not big fond of solving these things in class, but since you guys don't open books, I'll give you an example. Right? Any questions? Yeah, that's why I said open the book. There is a reason that now you'll go back and open the book. That's why I intentionally left it there, so that you can go back, and if I ask you to prove this, you should follow the steps. There is an equation given before in the book. Okay, so let's say the speed of, let's do this example, a jet aircraft has speed of, let me don't put the sign so that you don't get confused. Speed is, let's say, 550 mph at altitude of, let's say, 35,000 feet, and temperature is like minus 66 degrees Fahrenheit. So find the ratio of the speed of aircraft with respect to C. What is happening here? And this ratio is known as, right. Now this is, so far in the course, this is, I think, the third dimensionless number which we have done. First one was, that's a number, and I've told you it is not in the book, so better revise notes. Number 2 is Reynolds number, and this one is the third dimensionless number, the Mach number. This gives you an idea that if there is an object which is moving with a certain velocity, if you non-dimensionalize it with respect to the speed of sound in that medium, it gives you a good idea that how fast that object is moving, right? And that's what this example is about. So let's not put numbers here, but how would you kind of go over this problem? Is V given? It's given. So we are given this V, which is this one, right? And what is this? And C is, don't guess. 330 is like a 0 degrees Celsius STP kind of thing, right? That's why all this blah 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 stuff is given, right? So don't. Clear? And you should also know that if it is Fahrenheit, there is some constant number which you have in order to go for absolute temperature. If it is Celsius, you have to add something else to go to Kelvins. So Rankine, Kelvin, all these things you should know. Although I won't really go and test you on these things, but definitely you would lose points if you do not know some basic stuff. So that means the temperature is always an absolute temperature. It's an absolute temperature. And let's say I give you, where am I? Okay. So temperature comes from here. This is a constant. And K is? How do you know that? Book, or you just, everybody knows it by heart? Good. So once you, everybody knows these things, so let's hope everybody knows the answer as well. So the Mach number would be, and 550, it says mph, just to get you that it is like a 0.83 thing. So the aircraft is flying really fast. It's close to, it's not exactly, but like a transonic, it's very close to speed of sound. Good? Good enough? It is to some extent, but I have not asked you this. Some corrections are always there. This Laplace is kind of, is it in vapor pressure or in here as well? I have to double check this.
I think it was with
Errors?
I think it was in
I don't know. You might want to check. But as of now, whatever we have is, if there is any correction, I'll let you know if there is a special case. Okay. If either both the units should be the same, either go from mph to fts or fts to mph. In order to get it non-dimensional, you must keep the unit same. Clear? So this is a simple question, but expect something harder than this in your quiz or in your exams. Okay, so let's go to the next slide now. Okay, the next thing is vapor pressure. Right? What do you think? What is the vapor pressure? Okay, kind of. Okay. Anything else? Okay, so let's say there is a container as suggested. Here is the water. Right. So what happens is that since these molecules, they are randomly moving, right? Some of them, they have enough energy to kind of escape. Right? So they start to accumulate on top of the on top of the surface of liquid. And at the same time, some of them, they might be coming, where am I? Okay. And let's say the blue ones, they are coming back. Right? Clear? This one is kind of a funny heart-shaped molecule, but that's the way it is. So at some stage, what happens is whatever is going down and what is going up is equal, right? So yeah, it should be closed. I broke the heart. That's something which I have to figure out. I have to draw, let me circle straight lines, so it will take a while, and it's getting sweaty, and this thing does not really work well if you have too much of stuff on this. Yeah, I'll destroy it soon. Okay. Okay, so where am I? The speed is kind of slow. If you're teaching on this, then you have to be kind of go step by step. Okay, so let's write something which is given in the book. So let's write it so that all those who don't care opening the book have something written in their notes. Evaporation takes place because some liquid molecules at the surface have sufficient momentum to cohesive forces and escape into the atmosphere. So whenever there is an equilibrium condition reached, equilibrium condition is reached, then what happens? Number of molecules which are going up is the same as coming back to the liquid. So then that the pressure which is developed on the liquid surface is termed as this vapor pressure. Right? So far so good? Okay. So the next thing which is kind of affiliated with this is right. So everybody has its own boiling point. Right? You just push somebody and he starts boiling. Sometimes you just say something to someone and there he goes. So, but in terms of fluids, they have their standard way of doing things. Although their levels is also different. So different fluids behave differently once it comes to the boiling. Okay, and let's write something here. again from the book, which is the formation of vapor bubbles which is in from the vapor bubbles. Where is it? With an fluid mass. CR is having some issues. Question? I was going to try it. Engineers, do experiments. If your mom is not in the kitchen or not around, do it. And then what happens later, you might want to share, or you don't want to share. That's up to you. Somebody said pressure cooker. Good. That was something I was expecting, that somebody is going to say that. The boiling point goes high because of the pressure thingy, and then there is like an FSE kind of ideas that if you go to Murray, things get cooked early, later, or whatever the case is. So altitude, with the altitude, the density changes, the pressure changes. So those things, they matter, that they change the property of the fluid. That's what I'm saying. Try it. So if you think of it, if you have an airtight container, like a bottle of jam, empty bottle of jam, half fill it with water, and then you start to do it, then what will happen? हट जाएगा, नहीं होगी. Why? Air is compressible, by the way. You have sufficient air in it, right? Air is compressible. Increase करता रहेगा. So that means it would not boil. Okay, let's do this. Before you do experiments, there are some crazy guys who are doing things in the backyard. Right? Generally, they do things with the bike and all these things. But let's do it with a container. Initiated. It's a good thinking, by the way. I'm happy the CR is smart. Initiated. Okay, I was just holding everything. Let me complete this, and then you can make of whatever you are saying. Vapor pressure. Right. Now you will see that is the formation of water bubbles within a fluid mass, which is initiated when the absolute pressure in the fluid reaches the vapor pressure. What do you think now? Will it boil or no? Something to ponder for another 2-3 days. We'll meet again on Thursday, right? So, okay, there is something known as cavitation. Pointer options, just go to slide, let's say. And I'm sure this thing which cavitation. Yes, sir. Is it there? कहाँ पे है ये? FSE? right? That's what I'm saying, that this phenomena won't ever be discussed in the due course of time. It's a very complicated phenomena, right? The governing equations, what is the governing equation? I gave you the example right from day, on the very first day. We said and gave an example running to the gate and coming back. S equals Vt was the governing formula or the governing equation. Similarly, in order to do this boiling stuff, it is, we call that as a two-phase thing, two-phase phenomena, because now there is a liquid there and there is a fluid there. So the equations, the momentum equations, they become really, really complex, the momentum equation. That's what I'm suggesting, that these things we are not going to cover it in the class. But if somebody is really interested, they are very interesting phenomena from the viewpoint of for your higher education. There is a strong research area these days, which is numerical reservoir simulations. Numerical reservoir simulations. So all the oil and gas which is beneath the earth, few kilometers down. So what they do is they use supercomputers in order to simulate how things would be down below. So one of the big company guy, the ExxonMobil guy, he told me that each well which they dig is approximately cost them about $100 million each well, and the probability is, let's say they dig 10 or 12, one is a successful one. They get oil or they don't get oil, or they get gas or they don't get gas. So you can see the kind of complexity which is involved in doing physical drilling, and even before doing it, they want to make sure that using this computational technology they can kind of predict things. So once it comes to simulation, you require some governing equations, how things would behave at those temperatures, those pressures, so simulate those conditions. So things get really complicated even once it comes to simulating boiling. So these are complex phenomena. Cavitation, we have already, just on boiling we have spent so much time. So cavitation is something, again you want to go back and Google it, but I'll tell you one thing. Submarines, they have a propeller at the back. The biggest damage to them is caused by these cavitations. Cavitation is these bubbles, they are formed in let's say water, and then they go and kind of burst. So those fatigue, you know, understand fatigue? A constant or repetitive kind of cyclic stresses are being generated on those blades. So those small, although it seems that it's a small bubble which is causing an issue, but that is one of the big reasons of causing failure to those blades. So cavitation is another phenomenon, just like boiling, vapor pressure, cavitation is another one. Okay, another interesting thing is, and I have surface tension. And there are, rather than wasting time on watching some other YouTube videos, I'll strongly recommend go to www.youtube.com and write surface tension. Some of the professors in some other schools, they are doing small experiments just to demonstrate what is a surface tension. Right? So that is in fact, let's write the definition, the intensity of the molecular attraction per unit length along any line in this surface tension, and typically this is given by like a sigma thing. And if I make a figure here, Now this is a water surface, and this one is open one. So let's say there is a molecule here, right? Okay, and you have kind of forces acting in each direction. So this is being hammered everywhere, the same pressure. Okay. So if you see the top